We can look at the distribution of our blood pressures. Again, if we use class width 10, this is the distribution that we get. This is a histogram of our blood pressures. And we can see that this distribution sort of tends to follow something which might be a smooth curve, kind of like the red dotted curve here. Now this curve isn't symmetric. There's more of it on this side than there is on this side. So we say that this curve is skewed to the left a little bit, as opposed to a symmetric so-called normal distribution, where we could draw a vertical line down through the center, and what's on the right and what's on the left should be perfectly balanced. Of course, I can't draw it that accurately, but the picture should give you an idea of what we're looking at. Other distributions, the binomial distribution. Now you recall from probability that if we take the number of ways we can choose 0 objects out of 6, or 1 of 6, or 2 of 6, and so forth, where the choices are made without regard for order, then we get combinations. Now the combination of 0 things out of 6 is 1, 1 out of 6 is 6, and so forth, and you should remember how to do that. That should be familiar to you, and you should have done some calculations with these numbers. So for example, if we flip 6 coins, there are 0 ways, or there's 1 way to get no heads, 6 ways to get 1 head, 15 ways to get 2 heads, 20 ways to get 3 heads, and so forth. If we graph a frequency distribution of what we get if we flip 6 coins a large number of times, it's going to tend very strongly to follow the same kind of pattern that these numbers do. So we could put 1 number in here, 6 in here, 15 here, 20 here, 15 here, 6 here, and 1 here. If we want to talk about the probabilities of these different numbers, well, if we flip 6 coins, for example, there are 2 to the 6th, or 64 possible outcomes, of which we could also get just by adding these combinations. Again, that's something hopefully that you remember. And we get probabilities. Okay, the probability of getting no heads on one flip is 1 out of 64. So we could regard this part of the histogram as not representing one occurrence, but representing a probability of 1/64. And this one as 6/64, and 15/64, and 20/64, and so on, changing the meaning. So that could be 1/64, 6 over 64, 15 over 64, 20 over 64, and so forth. Whoops, 64. In this case, this would be what we'd call a probability distribution, because the sum of all these numbers is 1. And we'll note that this probability distribution is closely represented by this nice symmetric bell-shaped curve. If we go to a large number of coins, then we can get a lot of different possibilities, and our histogram will more and more closely resemble just the curve. Now this is being drawn fairly sloppily, but each of these regions here can be thought of as lying very close to the curve. And in the limit, as we approach an infinite number of coins and a really large number of flips compared to the number of coins, this thing smooths out into what we call the normal distribution. And we're going to talk just a little bit about that distribution before too long. It's another kind of distribution. For example, if we roll a fair die, then we could get 1, 2, 3, 4, 5, or 6, all with equal probability, the probability being 1/6. And that's a uniform distribution. There's no preference for one result over another if it's a fair die. Now if we roll 2 fair dice and look at the totals, as you know from the probability, some totals are more likely than others. 7s are more likely than 2s when you total 2 dice.